This is lecture 43 of Condensed Matter Physics 1. Over the past 3 lectures, we have been doing discussion on semiconductor physics. So, in today's lecture, I will be solving some problems related to the concepts discussed there. Problem 1. This is taken from Rosenberg Solid State Physics. A high quality sample of germanium which is a semiconductor has intrinsic behavior. At 300K. If lambda inverse threshold, that means this is the lambda. If lambda is smaller than this, then only some transition takes place for continuous optical absorption is 5.5 times 10 raised to 5 meter inverse. Estimate the temperature rise that will result in 20% increase in its conductivity. Solution. So, you are given that this is an intrinsic semiconductor. That means there are holes in the valence band and there are electrons in the conduction band. Now, if you shine light on it, the minimum frequency that you need is such that E g should be equal to h cross omega min. So, minimum frequency before light starts getting absorbed in the sample is h cross omega min equals E gap. What you are given is lambda inverse, and that gives you E gap. A given threshold lambda inverse gives E gap. So, we can calculate the gap energy of this sample right away. So, E gap is going to be h nu or h cross omega min, which is h lambda inverse min, that is the threshold, times C. You plug in the numbers, This is given to be C, 3 times 10 raised to 8 times H, 6.6 times 10 raised to minus 34. Lambda inverse is 5.5 times 10 raised to 5, and this comes out to be 1.09 times 10 raised to minus 19 joules. That is the gap in this. Once you know the gap, then you can calculate the number density in the conduction electron for a given sample. The conductivity sigma is E n mu electrons plus E p mu p. Now, since this is an intrinsic semiconductor, if n goes up by 20%, so would p. So, we need an increase of 20% in n, and automatically gives 20% increase in P by raising temperature. So, what you want is that sigma, which is proportional to n or P, if that increases by sigma by 20%, n should go up by 20%, and n is some constant times T raised to 3 by 2 e raised to minus E g by 2 kBT. Since we are estimating, I can take this to be E g by 2 kBT. So, in this I am assuming effective mass of electron is same F as effective mass of the hole. So, this is only an estimate, so we can be off by 1 or 2%, it does not matter. Now, if you look at this expression, the majority of change, the large change would come from the exponential function of temperature rather than T raised to 3 by 2. Exponential varies much faster than any power of T, and therefore, I am going to estimate using only the exponential part. So, major change is going to be due to the exponential factor. So, estimate taking n to be proportional to e raised to minus E g by 2 kBT, and what I want is n at certain temperature T divided by n 300 to be equal to increase of 20%. So, it should be 1.2, and this would be equal to e raised to minus E g by 2 kB 1 over T minus 1 over 300, and that will give you the answer. E g I already know, kB I already know. So, log of 1.2 equals E g by 2 kB. There is a minus sign in front, which I will take inside the bracket and write this as 1 minus 300 minus 1 over T. E g is known, and so is kB. So, this gives T to be equal to 304 times 0.2 K. That is your answer. I would also like to check if the neglect of T raised to 3 by 2 would make large difference. If it makes a very small difference, then our estimate is correct. So, at this point we will conclude that delta T of 4K gives 20% increase in conductivity. and let us check that. So, suppose I took this 304 and recalculated the change in n using that t raised to 3 by 2 in front also. Check. Take t equals 304 and calculate n t over n 300, which is equal to t raised to 3 by 2 divided by 300 raised to 3 by 2 e raised to minus e g by 2 k b 1 over t minus 1 over 300. Take t equals 304. This gives you n t equals 1.224 and 300. So, this is an increase of 22%. So, we are not off, our estimate is all right. Maybe temperature would be slightly less than 4K, maybe 3.9 or something. So, 4K increase is a good estimate to say that the conductivity of this intrinsic semiconductor would go up by 20%, and that is your answer. So, this is a check, not much different from the desired result of 20%. Problem 2. This is taken from Kittel's book. Given a semiconductor with electron and hole mobilities mu n and mu h respectively, show that it will have minimum conductivity at electron concentration n 0 equals Ni square root of mu h divided by mu n, where Ni is the intrinsic electron concentration. Find the value of minimum conductivity. In terms of intrinsic conductivity. Notice in this problem, we are talking about what electron concentration would give you minimum conductivity. That itself tells you that in semiconductors we have a control over varying the charge current charge carrier density. So, I could calculate this and find out after that whether I should dope it with acceptors or donor atoms. Let us find the solution. So, conductivity sigma is E mu n plus E mu hole times the number of holes p. Now, what we have learnt from law of mass action is that number of holes is equal to some function of T divided by n. The law of mass action was Np is equal to C of T, some function of temperature only. So, if you increase the number of electrons, holes will go down. If you increase the number of holes, electron number would go down. So, now I can write therefore that sigma is equal to E, that is common, n mu n plus some C T over n mu h, and I want to minimize this. So, we say d sigma over dn is equal to 0, and at this value you should have d2 sigma over dn square should be greater than 0. So, let us first do the first condition. D sigma over dn equals 0 gives n minus Ct over, oh this is not n, mu n, minus Ct over n square mu h equals 0, and this gives n equals square root of C t times the square root of mu h over mu n. Now, square root of C t from the law of mass action is Ni, and therefore, N0, the one that gives you minimum conductivity, is Ni square root of mu h over mu n. The question I may ask here is, what kind of doping should we do to achieve minimum conductivity? Is it n type or p type? So, we have seen earlier in our lectures that generally mu h is less than mu n, and this implies N0 should be less than Ni. So, you do dope by acceptors, increase the number of holes, and that will give you the minimum conductivity. That makes sense. If you have mobility of holes to be smaller than mobility of electrons, to minimize conductivity you want more holes and less number of electrons. I left it for you to check that this is indeed a minimum, because the second derivative condition gets satisfied at this N0. Next, what is the value of this sigma minimum? So, sigma minimum is going to be E, and we have already calculated, which is Ni square root of mu h over mu n times mu n plus E, the number of holes, which is going to be equal to Ni square, that is Ct, divided by Ni square root of mu h over mu n times mu h. That is the conductivity, and you plug in the numbers, you get E Ni square root of mu h mu n plus E Ni square root of mu h mu n. Now, sigma intrinsic is equal to E Ni mu n plus mu h, because in intrinsic semiconductor P and n is the same, and therefore, I can write sigma min is equal to 2 square root of mu h mu n, E and I, which is nothing but sigma I divided by mu h plus mu n. That is your answer. Problem 3. This is also from Rosenberg, and it says the effective electron mass in indium antimonide is 0.01 times free electron mass. Then its dielectric for antimonide is SB. I have written AS. Antimonide is SB, so I should have its dielectric constant is 17. Estimate the ionization energy of donor atom and the radius of electron orbit. Solution: we have already learned that because of the dielectric constant and the effective mass, the donor energy is less. So, I can write mod of E donor, which is equal to 13.6 over epsilon square m E effective divided by m E. You plug in all the numbers and you get this to be 0.47 MeV. Then for the radius, again we use the hydrogen formula. So, radius of electron is going to be the Bohr radius in hydrogen times epsilon times Me over Me star, and this is 0.53 angstroms times 17 divided by 0.01, and this comes out to be 900 angstroms. So, imagine this: if you have the lattice constant of 2 to 3 angstroms, then the radius of electron is about, let us say, 200 to 1000 lattice constants. That is how loosely bound it is. These three problems were to do with the carrier charge densities and the binding energy of donor or acceptor electrons. The final problem that I am going to do is going to be on the tight binding approximation. So, we have done tight binding approximation in the previous lecture and solved an example for 1D lattice. So, this problem is going to be 1D lattice with a basis. and in that sense it is similar to phonon calculation with a basis. And remember, in phonon calculation we had the acoustic band when this was a single atom. The moment we had a basis of two atoms, we also got an optical phonon. So, here also I am going to get two bands. Equations are going to be very similar. So, here is the problem. Take a one dimensional crystal with each lattice point containing a basis of two atoms, and I am taking them to be different A and B. So, this is like this. Here is the lattice, and each of this lattice point contains an atom A and an atom B. An atom A and an atom B. And let me show these lattice points by crosses. The distance between the two lattice points is r. So, this is very similar to having two atoms that were vibrating in calculation of phonons, and this time we will be working with corresponding wave functions. So, here is the basis with each atom having its own wave function. So, this gives two sets of block waves. One is going to be psi, obviously depends on k, corresponding to A, x, which I am going to write as 1 over root n summation over j e raised to I k r j is j times r times phi a x minus r j, and same thing for B. So, I can just write that here, and this will be B. So, we get two kinds of block waves, and we want to now calculate the energy using these two wave functions as the basis. So, now what we are going to do is take the general block wave function as psi k x, which will be some constant C A psi k A x plus C B psi k B x, and find the minimum h, which I will call E as a function of k using this. So, we are still taking a tight binding kind of wave function, except now we have two block wave functions and we are mixing them. So, in that sense, this is a truly variational calculation. Why so? Because you see, in tight binding, when we just made one function, we fix that function. In this case, I am doing a minimization. So, this will be better. There are variations to this problems where you can take two orbitals on the same atom and so on, but right now I am just taking a basis. And the approximation we are going to make is use nearest neighbor overlap. And similar to the problem in phonons, you will find that atom B would have nearest overlap with atom A, not the B on the next site. Remember, when we had phonons, U and V were the displacement, and V was getting a force due to U from the next and the previous site. So, same thing is going to happen here, and you may want to go back and see the calculation of optical phonons also. So, to find the solution, what we are going to do is calculate the expectation value H and minimize this. With respect to CA or CA star and CB star. Let me write the Hamiltonian first. Hamiltonian is going to be for an electron minus h cross square over 2m del square plus sum over all the sides of V A of x minus r j plus V B x minus r j, because now at each site there are two potentials, they are arising from the two atoms. And what we want to calculate is the expectation value of this H with respect to wave function. Now, the setting up of the problem is quite easy. When you take the psi x and calculate expectation value of H, this is going to be C A psi A plus C B psi B. The way I have been writing it is write the K here to indicate it is a K wave function psi B H C A psi K A plus C B psi K B. So, this is going to be equal to mod C A square psi K A H psi K A plus C A star C B psi K A H psi K B plus C B star C A psi K B H psi K A plus mod C B square psi K B H psi K B. And it is in calculating these expectation values that I will be making use of nearest neighbor overlap and so on, whatever approximations we make. So, what we have now, the standard procedure, that the expectation value H is given as mod C A square, and the expectation value with respect to psi A I am going to call H A A plus C A star C B H A B plus C B star C A H B A plus mod C B square H B B. And I want to minimize this with the condition psi B equal to 1. And this I am going to write as Ca psi Ka plus Cb psi Kb, Ca psi Ka plus Cb psi Kb. I will write this approximately as, by neglecting the overlap between A and B atomic orbitals, or assuming they are orthogonal, I am going to write this as mod Ca square psi K A psi K A plus mod Cb square psi K B psi K B, and each one of these is normalized, and therefore, this is equal to mod Ca square plus mod Cb square, and I want this to be 1. That is the condition under which I will do. So, we apply method of Lagrange multipliers and minimize d by d Ca star of H minus mod Ca square plus Cb square minus 1 with the Lagrange multiplier E, the energy equals 0. And same thing with respect to Cb square, Cb star, and the equation you get, and I will leave this for you, is H A minus E, H AB, H BA, H BB minus E times Ca Cb equals 0. You want non-trivial solutions, so the matrix determinant should be 0. So, eigenvalue E is given by H A minus E times H BB minus E minus mod H A B square equals 0. This is all standard variational stuff. The tight binding approximation and whatever we do comes in calculating these matrix elements. So, now invoke tight binding approximation with nearest neighbor overlap. That is what we are going to do now. Now, let me make the lattice again. Here are these lattice points. I will make 3 of these units, A, and B. Let me write this. This is A, B, A, B, A and B. Now, again you may want to go back to the phonon calculation and see how we are going to take the nearest neighbor interaction. So, one interaction we are going to take is between B and A. B from one side is not going to interact with B from the other side, that is farther out. And the other interaction we are going to take is within the same lattice point between A and B. So, A interacts with B as far as different sides are concerned, and within itself whatever the calculation is going to give you. Now, let us calculate H A A. I am going to go a little quick over this because we had done this earlier. This is going to come out to be 1 over n summation j summation L e raised to I k R j minus R L phi A x minus R L H phi A x minus R j. Now, we said we are going to neglect A from one side to the next, because the A from one side to the next becomes not nearest, but the next nearest neighbor, and therefore, only same site contribution is taken, and this I can write as minus alpha A, as we did in the calculation for one atom per site. Now, I am going to calculate H A B, which is going to be 1 over n summation over j summation over L e raised to I k R j minus R L phi A x minus R j H phi B x minus R, this is L j. If I take next nearest neighbor, only one, the forward of B would contribute, and I can write this, and one of course within each site. So, I can write this as equal to, and keep in mind that the sum over j has been taken out and cancels and all that. So, one is going to be phi A at x minus R, let us say at 0, H phi B x minus R at 0, and the next term is going to be equal to plus phi A x minus R 0 H phi B x minus R 1 e raised to I k R. In the single atom calculation, we are getting cosine, but here I just get e raised to I k R. So, this I am going to write as minus alpha A B minus gamma A B e raised to I k R. Let me write the first alpha also to be alpha A A, just to be consistent. Similarly, you are going to get H B A, which is nothing but H A B star, and you can also do an explicit calculation. You are going to get this to be minus alpha A B, because alpha and gamma are real, minus gamma A B e raised to minus I k R. And finally, you have H B B, which is minus alpha B B. So, the energy now you calculate is going to be given by the determinant minus alpha A A minus E minus alpha A B minus gamma A B e raised to I k R minus alpha A B minus gamma A B e raised to minus I k R alpha B B minus E, determinant is equal to 0. Obviously, for each k now you are going to get two energies. So, you are going to get two bands. You put in the determinant and you get alpha A A plus E, alpha B B plus E minus alpha A B square plus alpha A B square again plus 2 alpha A B gamma A B cosine of k R is equal to 0. So, this is nothing but alpha A A alpha B B plus E alpha A A plus alpha B B plus E square minus 2 alpha A B square plus alpha AB gamma AB cosine kr is equal to 0. You can do the rest of the calculation. I think I did made a mistake. This is going to be, this is not alpha, this is gamma AB square. So, this is not 2 alpha. I am going to write the equation all over again. The equation is, the correct equation is alpha AA alpha BB plus E alpha AA plus alpha BB plus E square minus alpha AB square plus gamma AB square plus 2 alpha AB gamma AB cosine kr equal to 0. So, this is a quadratic equation in E, and you can solve it, and the kind of bands you want to get are now one band like what one obtains in the single atom case. In addition, there is going to be one more band. This is only symbolic, like this. So, 2 bands are obtained with a gap in between, obviously. So, this is like the 2 plane wave calculation we did in nearly free electron model. Now, we have 2 atomic states that are giving you block waves, and then we are diagonalizing the Hamiltonian or minimizing the expectation value of the Hamiltonian with respect to the coefficients that are used to make the block wave function. There are variations to this problem. You can have same atoms forming the basis. For example, it could be a diatomic molecule that could be sitting on the basis. In that case, you would have alpha AA equals alpha BB. So, that is one variation. Other variation could be that the distances between the atoms remain the same and the atoms become different. That is pretty much like the problem we just solved. So, this is tight binding with basis on each lattice site. Obviously, the bands are slightly better. Even the lower band is going to be slightly better than what you did with single wave function calculation. So, let me with this conclude today's lecture. What we have done today is problems on carrier concentration in semiconductors, the donor energy level, and tight binding approximation applied to a basis, to a crystal with basis. Have been solved. Thank you.